Okay, hello everybody. What is the derivative? What is the derivative? Well, I have to be more specific. Of a possibly nonlinear map of a map f from Rn to Rm at an input x, or at a point, we could say at a point x, the derivative at the point x. Okay, so actually, first it's maybe easiest to say it in words. The derivative is the linear map. It is the linear map, that's the most important part, that best approximates f at inputs nearby x. Okay, so the derivative is a linear map. It is a new map, and it's the linear map that is best approximately f. So if we plug in things nearby to x, we will get very good values from the derivative. And so in a formula, we'd say that f at x, well, plus a little bit of movement, so we're nearby x. We're not at x anymore, we're at x plus v. You know, if our input space is over here, and let's say x was here, well then we're at x plus v. Now this is the point, x plus v. And so we've moved a little bit. But because we have the derivative, then we know that this is basically equal to f of x plus the derivative d, the derivative of f at the point x, evaluated at v, at the movement vector. So the derivative is a map. It's evaluated at a movement vector, and it spits out a new vector, namely what we should add to the vector f of x in order to make this be approximately correct. So that's what it is in formulas. This is sort of the motivation. This is why we do it. Now, what is it actually? Like, how do I calculate this? Well, or really, what's the definition? So I'm going to say definition. Well, so df at x, this is sort of, we could have called it like f, or, well, f is already taken. We could have called it g, and it's a new map. So usually we write the colon and we take the input space is again Rn. The output space is again Rm. So it's the same input and output space as f, except it's not f. It's a linear version of f. It's an easier version of f. So yeah, same inputs and same outputs. Now we're going to call the inputs by a different name because we're thinking them now as movement vectors. And that's what we're going to input to the map dfx, or df at x. Okay, so this is just what we write, df of x evaluated at v. And now we have to define that. We actually have to define what it is. Just like we might have another map g from r to r, and we say, well, x goes to g of x. But then actually we have to define, like, what is g of x? And so we might say, well, that's x squared. And so we could have even just written x goes to x squared. But I'm showing you now that we name this thing, and this is just like g of x or f of x, except it has some more symbols, the d and the f and the x, and that's all to remind us that this is the derivative of the map f at the input value x. So that's why there's an f in there. Derivative is why there's a d in there. At the input x, because we're going to approximate nearby to x, it's only going to work well, this linear map is only going to work well near to x, so even x gets in there. And this is just the name of the map. Now what is it? It is the limit of, well, the change in output. There's the change in the output divided by the change in the input. H is a real number that we're going to let to go to 0. So I like to put that h is a real number just to remind me h is not a vector. So when we're dividing here, we're not dividing by a vector. Nobody knows how to divide by a vector. But we know how to divide by a real number. Now up here, this is going to be a vector because f of x is somewhere in the output space Rm. It's a big vector. And f of x plus hv, so f of x at a nearby, at some point nearby to x, namely x is plus hv away. That's again the output of this is going to be a vector. So here this input is a vector and the output is a vector. Here the input is a vector x, the output is a vector f of x. We're subtracting vectors and then we're rescaling it. We're just rescaling it by this real number which said how much did we move. So I'll say in words, h says how far we moved in the direction v, okay? At least in this limit. Now h will go to 0, so h will disappear, and that's how we're going to get the correct answer. Just like we did in the single variable calculus when you calculated limits of functions of one variable. Okay, but usually we're not going to actually calculate the derivative this way. There will be an easier way, and that easier way will be because the derivative is linear. So in particular, df at x evaluated at the vector v, well, that's df at x, and v is secretly, v1 times e1 plus v2 times e2 plus v3 times e3 or something. Like, v is the vector if it's in three-dimensional space and it has these components, but that's just v1 times e1 plus v2 times e2 plus v3 times e3. And so that's just what I wrote here. But then the linearity is going to come into play here. And all we're going to need is, well, we can pull out this v1 is a real number. Like, if v was 4, 2, 3, then v is really 4e1 plus 2e2 plus 3e3. And so I'm just going to pull out that 4 and then say df at x of e1 plus v2. I'm just going to pull out that number v2. Maybe it's the number 2. And I'm going to evaluate the derivative at the vector e2. So e1 is that one, e2 is that one, etc. For higher dimensions, we have e3, e4. And I'm going to finally pull out that third little number and have it scale the vector, which is output by the derivative evaluated at the vector e3. So we're going to see this later. But basically, all we'll need to do is calculate the derivative at these basis vectors, e1, e2, e3. And this will have to do with partial, the first variable. This will have to do with partial, the second variable. This will have to do with partial, the third variable. And sort of these first, second, and third movements. Okay, so did I answer what is the derivative of a map? In formulas, it's this linear approximation, this approximation formula, a linear approximation. And then there's the limit definition. This is what is really going on. But then what we're going to see is that the linearity of this derivative means that all we need to do is calculate it at these very, very special vectors, e1, e2, e3, e4. So, like, they're very simple. They only move in one of the dimensions. And so this is what's going to make the derivative easy to calculate, despite it having this limit. Okay. In pictures, what is the derivative? Well, if f, let's say f maps the plane to space. So here we have f goes from R2 to R3, and here's a picture of the derivative. So you know that it maps the whole plane, goes to some possibly curvy, weird surface in space. And then, so if x is somewhere like here, like let's say that's x, then f of x might be somewhere like here. So that's f of x. Okay, and then what is the derivative? Well, what we're going to do is, in this case, we only have e1, or sorry, we only have, we can move like this way, and that would turn us into some sort of curve like that on the surface. And what happens is if we move in the direction e1, then we're going to get some velocity vector, and that vector will be df of x at e1. So this is the picture. Now let's say I could move in the second dimension, like this green line, and then maybe that would become some sort of curve on this surface. And then the unit vector e2 is in that second dimension, and we can calculate df at x evaluated at the vector e2, and that's going to give us some other velocity vector. And so what is the derivative? The derivative is, well, so for example, this little square will then go to some curvy piece of the surface, but the derivative will map that square to just a combination of these two special vectors, and it'll just look like a flat parallelogram. So it won't necessarily be a square again, but it'll be a flat parallelogram, and in fact, the derivative maps the whole of R2 to this tangent plane. And this plane just exactly matches this curvy surface at that point, and it's tangent to the point. So this is the pictures of a derivative. It is a linear map that best approximates f at inputs near to x, which means it takes this plane. It's a linear map, so the output is now going to be a flat plane in 3D, the output space. And what plane? Well, exactly the plane that passes through the point f of x and is closest to this curvy surface, where that surface is the image of the nonlinear map f. Okay, so there we have the derivative in formulas as an approximation and limits, and then using linearity to actually compute it. We have the derivative in words. It's the best linear version of f. And we have the derivative in pictures. Here we see the nonlinear surface, the image of f, and here we see the image of the derivative.